So in this video, we're hoping anyways to cover characteristic reactions of aromatic compounds. And also, I'm hoping to get through the directing effects. That is, if there's a group that's already on the aromatic ring when it undergoes a reaction, where does the incoming group actually go? Where does it land on the ring, in other words? So I'm hoping to get all of that into this video. So the first two things that pop into my head when I'm thinking about reactivity, and since these are such stable compounds, realize that a lot of the reaction conditions are going to have to either be harsh or we're going to have to set them up for success, right? Such that whatever it is, since the aromatic group is not very reactive, the other species it's reacting with has to be, right? So the first thing I can think of is where the ring itself is going to behave like a functional group. So if the ring behaves as a functional group, we have to think about, let me get the word down before I start talking. It's hard to talk and write at the same time. If the ring behaves as a functional group, we have to think about the electronics involved, right? And an aromatic ring with its conjugated pi system is weakly electron withdrawing. So that has to be taken into consideration, especially if it's behaving as a functional group on another molecule that's undergoing a reaction. Meaning it's sucking electron density toward itself, but not in like a huge way. And so a few reactions that we can think of, we could reduce the aromatic ring, so catalytic hydrogenation. Now, because these are not as reactive as your garden variety alkene or alkyne, you're going to need some harsher reaction conditions, like maybe increased pressure, increased temperature, maybe doing this under acidic conditions. Or you could do a dissolving metal reaction. So these are reductions. I'll show you a named reaction where we're going to dissolve a group 1 metal. And we'll proceed through a free radical mechanism. It'll donate its valence electron to the ring. And I'll show you the mechanism, or the proposed mechanism anyway, for how we think that behaves. And then I guess, of course, we could think of the ring itself. If it's on like another parent, it will act like a weak electron withdrawing group. Electron withdrawing group is often just abbreviated EWG. An electron releasing group, so something that either through an inductive effect or through resonance with a lone pair of electrons can release electron density into the piece of functionality you hope to use. Sometimes you'll see that as ERG. But electron withdrawing group is basically letting you know that, hey, I'm sucking electron density away from your reactive site. So kind of like a fluorine or some electronegative element would do. And then the characteristic sort of celebrity reaction, I'll put a little star next to this because this is where we're basically going to just die on this hill, is an electrophilic aromatic substitution. And this is very often abbreviated EAS. In an electrophilic aromatic substitution, what ends up happening is the ring behaves as a nucleophile. So your ring is the source of electrons. So this is your nucleophile. But since these electrons are involved in a conjugated pi system, so there's a sort of uninterrupted cloud of electrons, and there is a pretty decent amount of stability. In other words, it's, got a decently low potential energy. The source of electrons isn't sort of like thick and rich. In other words, right? They're there, but it's relatively unreactive. So your ring in an electrophilic aromatic substitution is going to be used as the nucleophile, as the source of electrons to attack an electrophile. So what you need since the ring is relatively unreactive or stable, right? So like if something is stable, it is relatively unreactive, right? We need a great electrophile. We'll abbreviate that E plus. And I will use E plus just to keep things short and sweet while we're going through these reactions. So let's just jump into the first category so that we can spend more time on our celebrity reaction, the electrophilic aromatic substitution. So let's just get these reductions out of the way. So reducing aromatic compounds. Now on paper, you can do whatever you want, right? Theoretically, we should be able to stick this in a reaction vessel with some hydrogen gas and a metal catalyst, and then expect that we get an alkane out the other side, right? But then that doesn't happen. Your ring is pretty stable, and so if you're trying to do a regular catalytic hydrogenation reaction, you're probably not going to reduce the aromatic ring. So what you need is some harsher reaction conditions. So you'll stick this into a reaction vessel with excess hydrogen, a great metal catalyst, so something that's pretty active, and probably increase the pressure. So you can crank up the pressure in your hydrogen bomb. Sometimes you can increase the temperature if you have a less active catalyst. And we typically will see these reactions with the aromatic compounds, reducing aromatic compounds under catalytic hydrogenation done under acidic conditions. So for example, we could just take benzene. And theoretically, three equivalents of hydrogen gas, a pretty sweet metal catalyst. Platinum's pretty awesome. Rhodium works pretty well too, so this will be your metal catalyst. And then often what you'll see under the reaction arrow will be like 2 or 3 atmospheres of pressure. Room temperature is RT if you have a really good catalyst. And either H plus or H3O plus to indicate that you're going to do this under acidic conditions. And then theoretically, what you get out the other side is cyclohexane. You could also do a dissolving metal reaction. So this is going to be, I'll show you a birch reduction. So we'll again start out with benzene. We'll take some sodium and ammonia and some methanol. And what we get is this compound here. These are terrible bonds, Amy. Well, good enough. So plus 2 equivalents of sodium methoxide. So how does that happen? And so this right here is a named reaction. In organic chemistry, we're loaded with those. This is the Birch reduction. People will name things after themselves if they come up with the reaction. Sometimes the reaction is just simply named after the compounds involved or what you get as a result or whatever. So this is a dissolving metal reaction, and we believe it proceeds through a free radical mechanism. Some people say everything proceeds through a free radical mechanism, but this one right here, I'm going to show you the free radical, the proposed mechanism anyways, for this process. We'll start out with benzene. And the sodium is going to come in with its single valence electron and plop it, say, on that carbon there. We plop a free radical on that carbon. We're going to take these electrons, move them here, and we can take these electrons and plop them up here. So what we get is something like this. And then we can deprotonate methanol. Draw that rather suggestively for you. Going to grab that. That's going to leave. And then, of course, when the sodium gives up its valence electron, it becomes sodium +1, right? That's going to hook up with the methoxide anion. So you'll get your 1 equivalent there of sodium methoxide. And then this whole thing will happen again. I have my free radical there. Here, I've got 1 equivalent of sodium methoxide. If it helps, you can draw this like that so that you can keep track of your charges if you like. Sodium comes in again. Plops a valence electron there. This is going to again attack another equivalent of methanol. Can you imagine being the person who figured this out? Some reactions are pretty weird, I think. This undoubtedly was somebody who just, and so of course we're going to end up putting hydrogens. I'm not drawing them in, but we put those hydrogens on those carbons where we have the lone pair. Sometimes things just happen in the lab, and then you go back and you're like, wait a second, what? How do I explain that? So that second equivalent of sodium methoxide, right, comes from the second step in the reaction. So this is a dissolving metal reaction or a Birch reduction. Now, so we've reduced our aromatic rings, right? Now comes our electrophilic aromatic substitution. Of course, aromatic compounds undergo nucleophilic substitution reactions. In Chem 42, 44, we're not going to do those. They undergo a lot of other reactions. You know, we can oxidize them as well, or at least the functionality that we have on them. But again, in this class, electrophilic aromatic substitution and just reductions are where it's at. So electrophilic aromatic substitution. So the difference between reactions with just garden variety alkenes and then reactions with aromatic compounds is that with a regular old alkene or alkyne, the electrophile is going to add to the molecule, but with an aromatic compound, the electrophile actually, it looks like it just adds to the ring. So I'll draw out just a regular sort of generic reaction. It kind of looks like it's just adding to the ring, but it's actually taking the place of one of the hydrogens. So it's not an addition reaction. It's actually a substitution reaction. So let's just keep this super generic and say electrophile is attached to some leaving group, right? And if you missed that, I'm going to say this is the electrophilic portion. And this is the leaving group. You know how like when we were doing substitution reactions with alkyl halides, so the carbon that bears the leaving group is the electrophilic portion. The leaving group could be some halide, right? Chloride or whatever. And then this right here is going to be your nucleophile. But that's a crappy nucleophile because that's a really stable compound. So you have to sort of like beef up the awesomeness of the electrophile. That really needs to be hungry for some electrons. In other words, the nucleophile is relatively stable, not super interested in busting up aromaticity to attack some other molecule. But it can be done if that other molecule is looking good, right? So what you can do is you can say, well, I'm going to attack there. That's going to leave. But what do you get? So this, again, it looks like an addition reaction. But really what's happening, and we haven't drawn these hydrogens in, but every one of those carbons has a single hydrogen on it, right, to complete its octet. We add the electrophile, or whatever that was, the electrophilic portion of that other molecule, to the aromatic ring. We've pulled electron density away from that other carbon, so we have a carbocation right here. And what you have floating around in the flask is your leaving group, which would probably have a negative charge, right? And then the hydrogen that we haven't drawn in is there. Each one of those carbons will have one. But if we take that hydrogen away, we can put these electrons back into the aromatic ring. So then that hydrogen is history, and we have substituted it for the electrophile on the aromatic ring. So it's not an addition reaction, even though it kind of looks like one, right? So we have taken the place of that hydrogen. Every one of those carbons now has a hydrogen, except for the one that has E on it. That's the electrophile. We have substituted that hydrogen for the electrophilic portion of some other molecule. So what types of electrophilic aromatic substitutions are there? And I want to show you how to make a good electrophile just with one of these reactions. So very specific types of electrophilic aromatic substitution. We'll get that out of the way in the first one. Let's do a nitration reaction. I like to show this one mostly because people, if you're going to do this in the lab, a lot of students will get confused about why we're using two acids and one of them is the catalyst. It's sort of like not, it doesn't make a ton of sense. Like, why would you use two acids and how are they reacting with each other? I want to show you that because this, again, this aromatic ring is not like super nucleophilic. But in other words, we're going to be adding a nitro group to the aromatic ring. The overall reaction looks like this. So just take out, and for all of these, just introducing them, we'll just start out with benzene. Later on, I want to show you what happens if you, what if you had a substituent already on the ring and I'm going to put an NO2 on there? Like, where's it going, you know? So you might see it written like this, nitric acid. And then you might see catalytic or even just H2SO4. Sometimes we don't write the word cat in there, but it is catalytic in sulfuric acid. And then what you get is your aromatic ring with a nitro group on it. But like, what happened? Because that doesn't look like HNO3. And what was the sulfuric acid doing? Here's the deal. That benzene ring is a really bad nucleophile. It's not super reactive. So if we could turn the nitric acid into a great electrophile, then it might be worth attacking, right? So we're going to create, I'll do this in a different color over here so you can see. We're going to create a good electrophile. So I'm going to start out with the sulfuric acid. This is catalytic and sulfuric acid. So I'm just going to draw this rather suggestively, like sort of just the business end of this. And the nitric acid is going to come in. And we're going to grab the acidic hydrogen off of sulfuric acid. So what we're going to get is HSO4 minus, there's your conjugate base of the sulfuric acid, plus you're going to get this, which quickly can attack itself to create a good leaving group. And this likely happens all in one step. Or the OH oxygen might actually grab the proton. Nobody really knows what's going on, but this is just as good of a description as any. So you get water, and this right here is the electrophile. So this little beast is what the ring is going to attack. That nitrogen is looking for some electrons, right? So the ring then comes in. You can draw the mechanism for this reaction. And I'll do just this mechanism so that we're not wasting a ton of time. They all proceed in the same exact way. It's you attack the electrophile. So here's the electrophile. You attack that with the ring, the electrons from the ring. I'm going to push electron density into one of those oxygens. And there's a positive charge on that carbon, right? Because we pulled electron density away from it in order to form the bond between that carbon above it and the nitrogen. There's a hydrogen on every one of those carbons, and your conjugate base likely comes in and snags that. Because this is catalytic in acid, you have to regenerate the acid at the end. So what you have is an aromatic ring with a nitro group on it. And then, of course, your sulfuric acid is back again. So don't forget what this looks like. This right here is worth remembering what the structure of this group is. It's easy to write NO2, but this positive charge is going to be meaningful to us. That is probably one of the most electron withdrawing groups we know about. The nitro group is like an electron vacuum cleaner. You have that on a ring, and what you have done is deactivate the ring toward further electrophilic attack. So, like, if being a nucleophile, right? If I'm wanting to use that pi cloud of electrons and I've got that nitro group on the ring, those electrons are not nearly as available to attack some other electrophile. So when we talk about activating and deactivating groups, that's what we mean. If you have an electron withdrawing group on the ring, it is a deactivating group. We mean deactivating because it is sucking electron density away from the ring, and those electrons are what we want to use to attack some electrophile. If we have an electron releasing group on the ring, something through an inductive effect, perhaps like an alkyl group, or if we have something like a nitrogen or an oxygen or a sulfur, something with a lone pair of electrons where we can sort of activate the ring through resonance, then those will be activating groups. Electron withdrawing groups are deactivating groups, and they direct incoming electrophiles to different spots on the ring. So let's get through these reactions first, and we'll talk about the directing effects of the groups. So this sulfonation is, we're going to add a sulfonic acid to the ring. The general reaction looks like this. So you have just benzene or some aromatic compound. We will have sulfuric acid, and we'll just cook this up. This one needs heat too. I should put that in. These really do need to be cooked up. They are not super reactive. And what you get again, the sulfuric acid is going to react with itself. You're going to create a good electrophile, and this will be the product. This is also an electron withdrawing group. So these are electron withdrawing groups. Well, you know what? Let's just abbreviate it so that we can save time. So that's an electron withdrawing group. Same goes with that. So it's pulling electron density away from the ring, and that electron density is what we're hoping to use to attack another electrophile, if that's what we choose to do. We can put a halogen on the ring. So we're going to add a halogen, right? So either like chlorine or bromine or whatever. This is going to be interesting because we are going to take our aromatic ring and we're going to allow it to react with a halogen, and these things exist as homonuclear diatomic species, don't they? So if I have just regular old bromine, it's just two bromines covalently bonded to each other. There's really no polarity, is there? Because they both have the same electronegativity. So if that's a crappy electrophile, and just like that, it kind of is, right? This can be, you can attack that thing with an alkene. We saw, we can make up the epibromonium ion. We'll just take the, pi electrons in the alkene and go ahead and attack Br2, make that 3-membered ring, blah, blah, blah. We saw that, right, in the alkene chapter. Your aromatic ring's not doing any of that, right? It's just sitting there, super stable, not interested. But we can use a Lewis acid, and a Lewis acid, remember, is an electron acceptor. So I can use a Lewis acid like this to essentially turn that bromine molecule into a better electrophile. I'll show you what that looks like in a second. We'll just draw out the product here. So of course we're just going to brominate the ring. But what happened here? So we can set this up where we have a bromine-bromine covalent bond and a Lewis acid. So that is an electron deficient species, right? Sort of coming in to bond with the Lewis acid, puts a partial negative charge on this bromine and a partial positive charge on this bromine. We have sort of created a situation where the electron density in this covalent bond here has been polarized. So these electrons have been polarized using the Lewis acid. It's sort of like having your friend grab your hand and pulling you out of a party if they think you're in a bad situation, right? So like they're kind of yanking you in one direction. The aromatic ring comes in, sees that bromine with its partial positive charge, and it is a better electrophile than just bromine on its own. So then this is going to take off. And the same old thing happens again. We put the electrophile on the ring. We've pulled electron density away from that carbon. If you're wondering, you could, if you're only starting out with benzene, I could put this bromine on any carbon. Doesn't matter. I'm just choosing to stick to one side. I could have put it on the carbon below, and then the positive charge would have been on the other carbon, right? So this is not really that big of a deal. Again, with the hydrogen, floating around in solution would be your bromide. And it's worth noting that reestablishing aromaticity is so energetically desirable that this, even though that other bromine was sort of swimming around, sort of hooking up a little bit with the Lewis acid, the bromide coming in and taking that hydrogen away, even though bromide is not even really a base, right? Because hydrobromic acid is so strong, bromide is just neutral. But the fact that you have the ability to just even re-aromatize that ring, you could blink at that particular species and that hydrogen would go. So this is super fast. And this is slow. The slow step in this reaction is going to be breaking up the aromaticity. Reestablishing aromaticity is going to be super fast, energetically favorable to reestablish aromaticity. So we've added a halogen, we've added, and by the way, this is going to be another electron withdrawing species, but it's not going to be as nearly as strong as a nitro group. So this is weakly electron withdrawing. The halogens will be the one example when we go through the directing effects, where you have an electron withdrawing group and you're deactivating the ring, but they direct to a position you might not expect. So the electron withdrawing groups are going to direct to the meta position, which I'll explain when we go through those types of reactions. And we did that a little bit with the nomenclature. We know that it's a 1-3 relationship with the substituents. For the electron withdrawing groups, I want to show you resonance structures and help you understand why we think that might be happening. The data is what it is. We're just trying to rationalize it, right? The halogens, we noticed that they are weakly electron withdrawing, and so they're weakly deactivating, but they don't direct to the meta position. So we'll talk about that in a sec. Fourth type of electrophilic aromatic substitution. I'm going to lump two things together in the same category. We just saw a Lewis acid sort of in action, but I want to show you another type of reaction that uses them. And there are two reactions that are called the Friedel-Crafts. We're going to do an alkylation and a Friedel-Crafts acylation. So essentially, we're going to be creating a new carbon-carbon bond. With the alkylation reaction, so you know how like if you have an alkene, you can take an alkyl halide, so like ethyl chloride or chloroethane, whatever you want to call it, common or IUPAC. And your alkene would just attack that primary carbon and you would lose the chlorine, right, as chloride. Well, because the aromatic group is not supernucleophilic, we have to add a Lewis acid to pull electron density away from the carbon that we want to attack. So in other words, the aluminum is going to be attracted to the electrons in the chlorine, and when that pulls on the chlorine, it's going to pull on the electron density in this bond, just like we just saw with the bromine. And so then the ring will attack that primary carbon. So there's that carbon. So we have our ethyl group now, right? And the chloride will remove the hydrogen to re-aromatize the ring. So same thing up here. We'll have plus HBr. We don't often write the inorganic products, but it's there. So that's going to be an alkylation. We're adding an alkyl group. We are not using a protic acid for this. We are using a Lewis acid. We want this to be attracted to that so that we can pull on the electron densities and the electron density in this bond and put a partial positive charge on that methylene to make it hotter for nucleophilic attack. Since the aromatic ring is not super reactive, we have to activate the electrophile. We can do the same thing if we want to acylate. So I could use an acid chloride. I could use a Lewis acid again. Pull the electron density away from that chlorine as it's attracted to the aluminum. I'm going to put a partial positive, I already have a partial positive charge on this carbon, but it gets bigger, right, as we pull on the electron density in this bond. And that's going to make a better electrophile. The ring then attacks the carbon. Chloride comes in, takes the hydrogen away. And I have acylated the aromatic ring. So this right here is our acyl group. See how we have the carbonyl, whereas with the alkyl group, we just have like the methylene and then right the ethyl group. So if you have that carbonyl in there, we have what's called an acyl group. And we can do a Friedel-Crafts either alkylation or acylation by using a Lewis acid to pull electron density away from the carbon that we're hoping to attack, put a partial positive charge, right, on the carbon we're interested in attacking. So what if you started out with the ethyl group or that acyl group or a bromine or whatever, the nitro group on the aromatic ring? Because notice how every reaction we've done, we've only started with benzene. I mean, surely you're wondering what happens if there's another group on the ring when you start? Or, hey, what if you wanted to decorate an aromatic ring with a bunch of different groups? How do you set this up? Like, what do you do first, kind of thing? So it's important to recognize that not all of these groups are going to direct the incoming electrophile to the same spot on the ring. So let's talk a little bit about the directing effects. Of other substituents that might already be on the ring. So it's worth noting that when we're doing an electrophilic aromatic substitution, we are using the aromatic ring as a nucleophile. So we're using that as a source of electrons, right? So you're kind of hoping that those electrons are going to be available to attack the electrophile. It's already super stable, so they already aren't super interested in attacking the electrophile, which is why we had to juice up the electrophile in all of these reactions. So now take that into consideration and say, how could I most help or bolster the electron density or activate the ring toward attacking the electrophile? So if we have our ring and we have a group on the ring that has a lone pair of electrons, we imagine that group to be an electron releasing group, right? This is going to be strongly activating. So the nitrogen is going to be less electronegative than oxygen. The oxygen also has a lone pair of electrons, but since it's more electronegative than nitrogen, it'll be activating, but not as strongly activating as if we had an amino group up there. We are sort of showering electron density through resonance into the aromatic ring and activating it toward attacking some electrophile. We imagine that we could have an alkyl group up there, and through an inductive effect, we could activate the ring. So we're supporting the ring attacking an electrophile by putting electron releasing groups through either a lone pair and resonance or through the inductive effect, just remembering our intermolecular forces of attraction. Smack in the middle, we have benzene with nothing attached to it. So no electron releasing group. This is our standard. For which to compare. And then we'll start putting electron withdrawing groups on the ring. So I could have a halogen. I could put like a chlorine up here. That will be weakly deactivating. It's a weak electron withdrawing group. I can imagine another aromatic ring on there, right? I could have another benzene ring up there. It would be a phenyl substituent. It's weakly electron withdrawing, right? So weakly deactivating. Or I could have an acyl group of sorts. We'll just say R. That could be just rest of molecule. And then the beast, the nitro group. This is our strongest electron withdrawing group. This is going to be the most strongly deactivating substituent that you could have on the ring if you want the ring to be the nucleophile. It does not mean that you can't do an electrophilic aromatic substitution with the nitro group on the benzene ring. It just means that you're going to have an awesome electrophile, and you're going to have to understand that if you have one of those deactivating groups, with halogens as an exception, if you have an electron withdrawing group other than a halogen on the aromatic ring, you are going to be directing your incoming electrophile to a very specific carbon. If you have an electron releasing group or some alkyl substituent on the aromatic ring, you will be directing your incoming electrophile to different carbons than if you had an electron withdrawing group. How do we know this? Well, nobody really knows anything, but in the lab, the data suggests that we get very specific products under very specific reaction conditions in very specific ratios, and we work our way back to sort of rationalize why this might be. What we notice is when we have an activating group on the ring, we direct the incoming electrophile to the ortho or the para position. So ortho para directors. So what happens is you do this chemistry and you come out with an aromatic ring where you have two products or possibly three, and one of them is only like 1%, right? And then the majority of your product mixture is the ortho-para relationship between whatever group was originally on the ring and the incoming electrophile. So the way we can rationalize this is, since we can analyze the product, we can work backward and try to make sense out of where it came from. So let's pretend we're directing to all three positions and look at the resonance, contributing resonance structures associated with each position that's been attacked. So in other words, I'm going to just keep this to E+. That's our electrophile. So our aromatic ring is attacking the electrophile. And what you're going to get is a bond between the electrophile. And if we direct this to the ortho position, you get a carbocation there. So this will be ortho. I'll show you para, and I'll also show you meta. So if we direct to the ortho position, that's the 1,2 position, I get that as one of my intermediates. I can imagine then, through resonance, I can draw another structure here, push the electron density toward that positively charged carbon, form a double bond there, still have the electrophile, still have the methyl group. Nothing happened here. I moved the positive charge over. Do you see that? I can do that again to get another resonance structure. Still the electrophile is there. Nothing happened here. So these are my possibilities. These are my contributing resonance structures. In this particular case, I have a tertiary carbocation. Tertiary carbocations are pretty stable. So in at least one of my resonance structures here, my contributing resonance structures, and by contributing, we mean this contributes to the hybrid, right? I have a tertiary carbocation in at least one of them. What if I directed to the para position? So when we do chemistry on an aromatic ring that has an electron releasing group, we notice that primarily the majority of the product mixture is orthopara. So we draw a mechanism to try and rationalize it. So now I'm going to be, I could have been nicer about that. Hang on a second. I know it doesn't really matter because this is just a cloud, but this might bother some people. I'll use that bond. They're all the same. It's just a cloud, right? So I'm going to add the electrophile to the ring at the para position. Positive charge goes on that carbon. Again, this is all like faster than you can probably imagine, right? Because some conjugate base is coming in and ripping a proton off of an adjacent carbon, right? The one that your electrophile went onto, and re-aromatizing the ring. This is all the in-between stuff where we're trying to rationalize why a group went where it went, right? So we draw all these resonant structures trying to say, well, we get these molecules in the lab, and we're just trying to figure out why. Like, why is this like 1% meta, mostly para with a little bit of ortho? Like, what's that all about, right? So again, you see in that middle resonance structure, we have a tertiary carbocation. So here are your contributing resonance structures. We just moved the charge around the ring by delocalizing the electron density. Here is another tertiary carbocation, which is considered to be pretty stabilized, right? Because we have that alkyl substituent up there attached to the carbon that bears the positive charge. So just like we said before, in order of increasing stability with the carbocations, right? It goes methyl is the least stable and a tertiary carbocation is the most stable. So in these resonance structures, we have at least one contributing to the hybrid where we have created a tertiary carbocation. In all, reality, we end up saying, hey, we got an orthopara majority, major product in the lab. This could be a pretty good explanation as to why. But only after you attack the meta position and compare, right? So let's do that. I'm going to put that electrophile at the meta position. So what you get, it doesn't hurt to practice drawing these out on your own. Once you get the hang of this, a lot of our rationale comes from drawn out resonant structures. So here's one. You can draw another one. So the electrophile is still in the meta position here. Put the double bond there. Do it again. None of my contributing resonant structures is giving me a tertiary carbocation if I put my electrophile in the meta position. So all of these are secondary carbocations, and we believe that the tertiary carbocation, just data suggests that those are more stable. We also, in the lab, if we put this reaction to the test, come out with the ortho-para mixture being the major products. It's not saying you won't get any meta. It's just to say that it's probably less than 1% or something really small like that. So this is if you have an electron releasing group. So a methyl group, a hydroxyl group, an amino group, something like that. Then we have the meta directors. So if I have an electron withdrawing group on the ring instead, I'm primarily going to direct the incoming electrophile to the meta position. So with an electron releasing group, these are going to be the positions that we direct to. So this is for an electron releasing group or a group that activates the ring toward attacking an incoming electrophile, and also halogens. That's an exception. So they are weakly deactivating, but they are ortho-para directors. Electron releasing groups are activating, and they are ortho-para directors. If you have electron withdrawing groups, like the nitro group or some acyl group attached to the ring, you're going to direct to the meta position primarily. So we'll just use the best electron withdrawing group. This is where it's helpful to remember there's a positive charge on that nitrogen if you draw out the structure. If we attack the electrophile and put it at the meta position on the ring, that means it's in a 1-3 position to the nitro group. We'll go through this just like we did before with the other, with toluene. So there's one, right? I can push the electrons around, come up with another hybrid, or another contributing resonance structure. We can do this again. Don't forget the nitrogen has a positive charge. Or you could have an acyl group which would have a partial positive charge. So if you direct this to the meta position, you get at least one carbocation. So of course you're getting secondary carbocations all around, right? But you get at least one where the positively charged carbon is across the ring as far away from the electron withdrawing group as possible. So this right here puts the carbocation as far away from the electron withdrawing group as possible. The nitro group has a positive charge on the nitrogen. Putting that carbocation as far away from it as possible is energetically desirable, we believe, because when we do these reactions and you have an electron, withdrawing group other than a halogen on the ring, the major product is the meta product. What happens if I were to put this incoming electrophile at the ortho position? So again, you could draw these. It's not bad to get practice with this. Feel a little bad ruining all your fun here. I'm drawing them all. But we can do So this will be ortho, then we'll do para. So ortho's here, which means that I put the positive charge there. Again, I can move the electrons around to get another contributing resonance structure. And again, but look at this one. If I put this at the ortho position, I have at least one contributing resonance structure that puts the positive charge right next to the electron withdrawing group. That's bad news, right? We believe. So this puts your carbocation, even though it's a tertiary carbocation, you're putting that positive charge adjacent to the electron withdrawing group. And the nitrogen has a positive charge. You're bringing two positive charges near each other. That's terrible, right? Energetically speaking. There's a coulombic force of repulsion going on there. So when we draw out the resonance structures, we're like, okay, this could be one of the reasons, or it could be like the best reason, who knows, why you don't really get the ortho substitution when you have an electron withdrawing group. And the last one would be if we were to attack at the para position. So again, electron withdrawing group, we have our ring, we put the electrophile at the para position. There's one secondary carbocation. Move the electrons around, come up with another contributing resonance structure. That puts a carbocation right next to your electron withdrawing group. Considered energetically undesirable. And again, at the end of the day, when we do the chemistry, we notice that when we have an electron withdrawing group on the aromatic ring, the major substituted product is at the meta position. And then we draw these out to sort of help rationalize it. So again, this puts positive charge adjacent to the electron withdrawing group. The coulombic force of repulsion, we believe, is energetically undesirable. So at the end of the day, what you get is what you get, and this is what we do to try to rationalize it. Very often we draw a bunch of resonance structures. So if you wanted to put a few groups on the ring, say somebody wanted you to make very specifically or they say, you know, design a synthesis or pick the order in which you would add these reactants. So you want to make, say, so you want to start out with benzene, and you want that from just benzene, right? Which group would you add first? So first thing you want to do is note their relationship, right? This is meta. These groups are in the 1-3 position to, you know, relative to each other. So then you have to ask yourself, which one of those groups is going to be a meta director? Is it going to be the sulfonic acid, or is it going to be the hydroxyl group? The hydroxyl group is, I'm going to do this in different colors to help out. This is an ortho-para director. Right? It's an activating group. It is an electron releasing group. Write down everything you know about these groups, right? It helps. So then you could have as many different substituents on the ring as you like. You just from here are saying, this is what this group is going to do. This is what that group is going to do, kind of a thing, right? So even if I want to put a third group on the ring, right, depending on where I wanted it to go, I know these things about these groups. This is a meta director. It's deactivating. It's an electron withdrawing group. So if that's a meta director, put a little hyphen there for you. If that's a meta director, wouldn't that be the group I'd want to put on the ring first? So if I get that group on the ring, then when I add the hydroxyl group, it'll go to the meta position. If I put the hydroxyl group on the ring first, then the sulfonic acid is going to be going to the ortho or the para position, and that you won't get this relationship that you're looking for. What if I wanted to put a third group on there? What if I wanted to put, like, I don't know, a chlorine and I wanted it to go, I don't know, next to the hydroxyl group, right? What what would I do then? Would I start over from benzene and put the chlorine on first and then put the hydroxyl group? Probably, right? Because those groups would be orthopara directing. So then I could get the sulfonic acid next to the halogen, right? If I put the halogen there between the two groups in the first place. So you kind of just have to ask yourself, like, what do you want to end up with? And what do each of these groups sort of bring to the party, electronically speaking? We know that if we have an electron releasing group, it's activating the ring toward attacking the electrophile. And after drawing all these resonance structures out, we've tried to convince ourselves why those electron releasing groups are orthopara directors. Same goes with the meta director, right? The electron withdrawing group. Or if I have a halogen on there, halogens are actually electron withdrawing, but they're orthopara directors. So we have to just keep that in mind. That's the exception. So you have to look at what you have and decide what order you would put the steps. So it's a typical homework question, typical exam question, something worth noting. Work through each of the groups, figure out what's going to happen electronically, and design your synthesis accordingly. So these are our aromatic groups. These groups that we have, so specifically here with the phenol, so with the hydroxyl group on the aromatic ring, I'm going to save discussion of that and the one with the amino group, aniline. I'm going to save those for the alcohol and the amine chapters. They're very special. They're not just your regular old alcohols or amines. They have that phenyl group attached to them, which is weakly electron withdrawing. So phenol is not the same as, cyclohexanol in terms of reactivity. So talking about very specifically phenol and aniline, I will leave those to the alcohol and amine chapter. But this will do it for our aromatic compounds. This is as far into aromaticity as we're going to go in Chem 42 and 44.